now we went from the very small part of the cell to the electric fields around the cell, summation of the cell. So let's go the final distance to how they actually get out of the head and what that means. So this last part here is kind of how the bioelectric fields behave when they are inside. I do like this, yeah. Getting tired of. Yeah. 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 Then. Yeah. No, now it's not nothing. Yeah, so it's all the way up. Yeah. Okay, I'll just try to speak a little louder. Now I also had some coffee, so now I'm warmed up. Right. So the electric currents, this should come to no surprise that we're looking at, is happening inside the head, and the head we can kind of imagine as a sphere. So this participant here, we could say that this volume here is representing the head with everything inside it, and then we have the electric field. And if this was just a closed sphere with a vacuum inside, these electric fields would just propagate. And what we could measure from this field inside the volume is then how this field look at the outside of this sphere. And in principle, that is what we do with EEG. Where, of course, it's not just a sort of physical ideal state, it is the real head. But actually, to understand the physics of the electric fields in the head, a sphere model like this is actually a really good physical approximation. And so that in source modeling, and so these just modeling the head as a sphere can actually give quite good localization. So just from this, try to understand how the electric field propagates throughout the head. And when you have an electric field, so I have to look at my notes here. You have an electric current represented by J here going in some direction. The pluses and minuses here represent like kind of the charges in which direction they're going, but it's the red and blue arrow here that's interesting. So the electric current is dependent on the resistance and the electric field that it's so the sigma here represents the conductivity, and the E is the electric field. Then the current is the current represented by I. Here the arrows mean that it's having a direction. Is the electric current density over the or in this area of some kind of material. So this would be. So what is relevant for understanding how the electric currents propagate throughout the brain is this concept of resistivity. So you can see that's the inverse of the conductivity of the properties of the material that the electric field is propagating through. And so this applies to any electric field, whatever it is. You would find it if you are working in engineering or so. But why this is relevant is because inside the head we have different types of material, from skull to soft tissue, skin, CSF, and so on. All these different types of tissue types had different conductivity, different conductive properties. So this kind of cartoon again represents that we have our pyramidal neurons somewhere in the cortex that the electric field sums up. But for all these electric fields to kind of transverse up to our electrode, represented by this up here, it kind of have to pass through all these different types of matter that we have. So say if this is the brain tissue, we could have like a layer of CSF that is a saline solution, so it had actually a really good conductivity. But then it would meet the skull, for example, that had a very high resistance, meaning that it has a very bad conductivity. which meaning that less current will then be able to flow through there. And the same with the different type of tissue and until it reaches the scalp. And this means that when we measure the potential at the scalp, the field would be distorted relative to all these different types of materials and how the conductivities are. So the conductivities of the materials, and of course the actual shape of the head, the density of the skull, the different layers that people have. And here, all heads, even though we have the kind of same things, comes in different shapes and sizes and so on. So this is a simulation I have borrowed. So saying that we have a strong dipole here somewhere in the middle of the head, and based on some sort of biophysical realistic measurements of what the resistance would be, this would be how the electric field actually propagates throughout the brain, kind of assuming that's a single dipole here. And what's to be aware of here is that we see that in the kind of inner part of the brain here, we have a very good propagation of the electric field. So the warmer color, the more current density there will be. But what might be a bit disheartening is that when we look around at the scalp, we see that it's basically blue, so there's not much of the original electric field left when we get out here. And that's due to the different, both taking into account the conductivity and then how the shape of the head here also disform these fields. And this is one of the reasons why we generally say that EEG has a low spatial resolution, because once we measure it outside the head, the signals have been distorted in this way, so we don't really, they will be spread out quite a lot. And we can kind of illustrate this. So we have a participant here with sort of standard MRI image, and we can then say, like, it's very, if we want to do some source modeling, we would compart it into this. So we have different layers in the head here, just representing the brain, the skull, and then outer soft tissue, like only around the scalp of the head here. And then all these would have different conductive properties. So say we have a dipole somewhere here, so this is again just a toy example. If we say it's just spread evenly inside the head, we would get like a positive and negative kind of direction of the field. Remember, it was just spread out. So we see it from the side. So we have over here a strong positive side of the field, and over here the negative side of the field. But then what I try to illustrate here is that it would then reach the skull, and then it would, because the high resistance in the skull, the current would be fractured much more. So one way to think about this is the same way that if you have a pool of water and you would be to put a stick down in it, due to the fraction of the light, it would look like the stick is bending underwater. It's kind of the same physical principle. It's not light that is being fractured here, but it's the electric field, which means that when the high resistance, it would be spread out more. And so now reaching the scalp layer, it would be scattered out again to another degree, which means that even though we had here like a single dipole in a very specific area, we would basically see it kind of spread out over the whole scalp, so giving that is sufficiently strength of it. So that means that when we measure EEG at the scalp, so say we measure now here from the front of the head, we have put a cap on and have all the different, here seeing the scalp topography. So here imagine that you're seeing the participant from the top down. These represent the ears, and the triangle here the nose. Each dot here would be an electrode. So saying this position here in the front would probably correspond to some measurement that we're doing around here. Then we say look at the measurement that we're doing just slightly more to the back. We see we're moving away from the darker blue towards the more lighter blue, meaning we're moving from the strongest negative pole of it to the more towards the midline, which we see when we are kind of in the middle, it's close to 0. So the colors here, when it's greenish, is close to 0. And as we move towards the back, the red here would mean we are now moving to the positive part of the field. So even though we had this single location in the brain, what we measured as the scalp was actually covering basically most of the head in this example here. So if we were just to look at a scalp topography like this, so this is a very typical, this is some data measured long ago. For a very simple stimulation, you have this dipolar pattern at the scalp. So we say we probably have activated something that represented quite good as a single equivalent current dipole. If we were to look at this topography, where would you think that the dipole is located? So we have the blue part. Yes, I think that's a really good. Yes, but actually, when we think of a dipole, it has a positive and a negative part. And sorry to say, this is a trick question, because the best guess would actually be that it's located around the 0 line when we see it here, because we would then kind of anchor it there and then point in this direction that it's, now in this example I centered it on the middle, but that the dipole is located at the X, but have the strongest negative would be pointing directly backwards from the dipole, and the strongest positive would be pointing directly forward. So other way. In this example here, you can kind of thinking it as kind of a jet engine. So you would have like the turbulence, the air flowing in one place. You have a very strong influx. So that would be the where you would have the negative potential, and then you kind of have the stream going out in the opposite direction, but kind of flowing with the same strength. And currents, electric fields are kind of in the same way that you have the current kind of flowing in and going out the other way. And if this were a like perfect ideal case with no resistance, it would just go on infinitely. But since we have the different materials in the head, so when we see these two kind of roughly a dipolar pattern, a good guess would be that the source is in the middle. So this could be called like eyeballing source reconstruction of it. But that is actually a bit dangerous, because just looking at the scalp topography, seeing how much it could be spread out here, we are not so precise. If I didn't know exactly where the signals should be, but I might be more hesitant to do this. And this is due to something that's called the inverse problem. And that's, I guess, as a fact of physics, that basically says that for every kind of topography that we measure, like outside of a volume, there could be many different kind of configuration of the sources that could give rise to this. So going back to the idea that we have that all the currents can be summed up, just similar to how vectors are summed up. I said that in this case here, like a single dipole, where we measure like the negative and positive of the field, which I tried to illustrate with these colors here. They're quite faint, but I hope you can see them. So having the positive and negative side of the so this would, just for a single dipole, be very logical. But we could also say maybe it's actually two dipoles that are kind of arranged in this way. They would sum up the two red arrows to actually be equal to the red, or to the now gray arrow here. Which means that they would actually, looking from outside the scalp, generate the same field. Or I could come up with some kind of really crazy, not plausible at all, but from a purely physical, mathematical perspective, this configuration is would also generate the same scalp field in this case here. So the inverse problem basically states that for any measure of scalp potentials, there are an infinite number of possible underlying configurations that could give rise to this specific topography. But does that mean then that when we're measuring things at the scalp, we don't know where things are going on at all? Maybe in a ideal physical sense, yes. But since I'm not a physicist, come from neuroscience, we are allowed to make some assumptions about what is going on here. We can kind of make some assumptions. And one is, of course, we know that the summation of currents that we measure comes from the pyramidal neurons. So a configurations where everything was like this is very biologically implausible. So we can start by making some biologically plausible assumption about where our currents are coming from. It does mean that we cannot map one-to-one from scalp to underlying sources. The spatial location can be deceiving, but if we see a single dipole, like in the plot showed before, we can also apply some, I think, basic logic, Occam's razor, saying that perhaps we should just accept the simplest explanation and kind of lack of conflicting evidence. And here I think a good thing when we look at scalp topographies is always take our prior knowledge into account. So if we know, for example, I do a simulation of a visual stimulation, I would expect that the first signal that I would measure was from the visual cortex, because that would basically what everything we know from neuroscience tell us. If the first signals show up in the frontal areas, I would have a very strong indication maybe I did something wrong, probably put the cap on backwards. So it's good to basically, when we design experiments and think of EEG signals, to take our knowledge into account. It's also stressed that later, the importance of experimental design, that we actually try to design experiments that target some signals or some areas that we know to be engaged, so we kind of can zoom in and think of where we want to look at the signals. But this also means that when we are dealing with, so just saying we don't know anything about the underlying sources is too harsh, even if it's kind of mathematically true. But we also know that the brain is kind of a complex organ, and a lot of different processes are going on all the time. So thinking that just one small patch of the cortex is kind of active at any time point is also an assumption that we know is wrong. We know that the whole brain is active basically all the time. We cannot shut it off. And this plays into kind of the next thing that we need to be very aware of when we think of that, is the superimposition of sources. So far I've just very simply said there was a single dipole in the brain and how this propagates throughout the head. But these single dipoles are, under some circumstances, we can see this kind of activity, mainly in kind of primary sensory stimulation. But as soon as we start to look at more complex processes in the brain, we will have different areas of the brain being active. So someone was working with memory, and memory, I think, is a good case of there isn't kind of one place in the brain that represents memory. Memory itself is a result of a network of the brain that is going on. There might be some areas that we know are central hubs, but there's not like a memory area of the brain. So in most cases, we would have more than one source. And there's a red and a blue one here. And similar to before, where the electric field would propagate, now it would do the same for both of these. And at one point, they would kind of cross over each other and be summed up. So similar to the summation of currents, when we started looking at this, the electric fields from single neurons, actually when we're looking at the macro level and the summation or more equivalent current dipoles, they also just sum up in the same way. So what we would measure at these two electrodes that we have put here on the scalp would be a mixture of these two sources. So this example here, it's I think it's taken from the book by Steve Locke that I also recommended. I think if you really want to dive into to ERP research, this is a really good place to start. But in this simulation here, they have put sort of 3 electrodes around the scalp. I think this is supposed to be at the back of the head. And then they simulated 3 dipoles located in the brain. So this is a head scene sort of in the cross section here with the midline, and this is supposed to be the cortex. So calling these different source C1, source C2, C3. This is just a simulated example. So in this example, they have different time courses of the different sources. So how active these would be, represented as a single dipole up here. So what we can think of how it is measured at these 3 electrode locations, E1, E2, E3, is that it's basically a linear mixture of these 3 signals. And the mixture is given by these, this W, that is just a number of weights. And these weights, in this example, you can think of as how much the signal from the source where it is is attenuated based on the different material and tissue it has to traverse into it. So one that is further away would have a little lower weight because it would have to, there's some decay of the electric field and have to pass through more matter before it reaches the electrode site, but it would still reach it to some extent. So what we measure is just the summation, like each of them multiplied by the kind of forward weight, and then summed together. So when we would measure at different sites, we would see these different signals. And what is also here that see that they could, even though they're generated by the same sources, the waveforms could look very different depending on where we are, because the kind of shape of them is also dependent on the kind of orientation. So of course, if you have one here that is more towards the positive side of the field, it would measure so this C3 as a positive component, whereas with its towards the negative side of it, it would measure kind of the same component, but with a negative sign, because it's basically on the opposite side of the dipole here. And here they have like 3 sources to illustrate this, but in reality it's more smooth. So we have different patches of the cortex are active, and how much we actually get this summation can be quite it's a bit fluent. Yes?
Sorry, I noticed that the deflection for this, the positive is at the top, in contrast to the EEG.
Yes. I think because here it's not the voltage, it's the current density that is measured. And because I think in this book he specifically says in the introduction that he thinks this idea of plotting negative upwards is an artifact, so he consequently does it the other way around. That's why I say when you look at the figures, always look at the axis, because it's not consistent, unfortunately. But that's a good point. Okay, so this summation of currents also can lead to some curious cases where we might see a pattern. So for example, seeing a very strong dipolar pattern that is actually caused by 2 underlying dipoles. So this kind of inferring to the simplest solution might not always work. So in this case here, there are 2 dipoles somewhere in the cortex. But since they, in this case here, are pointing in the same direction, or pointing towards kind of the same point here, then you would have the positive side of the field of both of them going in the same direction, which means that you basically sum those up. So it would look like there is a very strong positive field here, but it's actually 2 fields that are summed up. Whereas in this case here, where they're kind of pointing in the other direction, so now one has a negative field in this direction and a positive field in this direction. And if we were to assume that these are like the same strengths, so one would have a very high positive, one would have a low negative, and the summation would be 0. So here, if I didn't know about how many dipoles I was looking at, I would say, oh, there's a very strong positive over here, negative over here, then maybe I have a very strong dipole in the center of the head or something, but that is not true. So scalp topographies can be a bit deceiving. I think this is, I like this study. It's a bit complicated, but I'll just give a simple explanation. So they are looking at how alpha wave activity also are getting mixed together. So they did a simulation of a brain sort of based on a realistic physical approximation of the head. And then they put some alpha activity. So we have the visual alpha, that is like the classical EEG from the very first EEG recording. But we also have alpha that comes from the sensory motor area, from the parietal area, and from the temporal areas. And so they put some dipoles in here and simulated some alpha activity. So to try to estimate how much relative contribution on our electrodes, so all the gray dots here placed on the scalp. So how much would they pick up of these different types of alpha? And they gave this as a kind of response to people saying, oh, we are just measuring like this type of alpha, visual alpha. And so to see what, if you're saying you're measuring visual alpha, how much are you actually picking up alpha that isn't from the visual, but perhaps from the temporal areas, or the other way around. So they color code them here, so kind of blue, yellow, red, green, depending on the source of the alpha oscillation. And they then simulated just what would be equivalent to some resting state EEG measurement. And what they showed here, saying this would correspond to, as I said, with an eyes open, where you kind of have a bit of a suppression of the visual alpha. But what I think is really striking in this figure here is that the purple colors, so the occipital alpha, you actually see that it makes up quite a large percentage. So each of these pie diagrams represent the percentage of the signal that this electrode would pick up. And you see that even at the frontal electrodes, so you have a very strong contribution from the visual alpha. So, for example, if someone was to say, oh, we took this electrode to represent visual alpha, this electrode to only represent temporal alpha, we see that here maybe about 30% of this at the temporal electrode still represent visual alpha, just because of how the field spread when we measure it at the scalp. And I think the main argument was then that when we do the eyes closed, when we have a great increase of visual alpha, well, it basically, you see it looks almost completely purple. So, so the visual alpha basically dominate all other, just because the strength of the signal is so strong that it drowns out. So knowing that there is this, this propagation of the signal and this summation at every electrode that we measure, I like this because it kind of shows it as percentage how much signal would be picked up. Actually matters a lot from when we start to make conclusions. So if I was interested in temporal alpha, I might, well, first of all, not use an eyes closed paradigm, but do surely for eyes open, where at least have some more signal. The problem is, of course, that in real EEG recordings, we don't know this mixture here. This is a simulation, so they, of course, can control all the underlying physics. But when we do EEG measurements, we only measure the scalp. Everything beneath is, we're kind of blind to that. So why is technically not under the, oh yeah, so when we also measure something, like an ERP signal, we usually would measure some response to a stimuli, and that would come out like some waveform that could look something like this here. And we might have an idea that it's generated by some specific area of the brain. It could be like in the sensory motor cortex here. We do some sensory stimulation. And we know that once you stimulate, say, a tactile stimulation of the finger or something, it would pass through the periphery, to the thalamic relay, and to the cortex. But we also know that, well, why did it read at the primary sensory areas? I think all of you have seen this homunculus figure with the giant hands and the tongue. And so that we know these things map to, but it doesn't stop there. It's kind of also processed further on in the stream, which means that there might be sort of separate areas or separate sources. In this example here, there would be 3 sources that kind of process this information. So what we measure at the scalp, again, would be a mixture of these underlying sources. So this would be one example that these 3 sources kind of sum up if we were to measure it here to what we measure there. So the scalp waveform is a summation of the underlying sources or components. But it's also possible that it could be, again, since we don't really know the truth about what's going on here, it's also possible that there could be more different sources, again, that could sum up and give us the same scalp potential. And I'll return a bit to how we can deal with this in experimental design in the afternoon. But that means also that when we look at our measurement at the scalp, we should be careful to not make bold statements about now, because I see this peak here. It has to be this area of the brain or this underlying thing that is responsible for this, at least not without having some other prior information that I can use to kind of reinforce this, this notion. Okay. So saying this is kind of the same physical principle. Usually not call it the superimposition of sources here. That would be the mixture of this. But actually, when we do a measurement of EEG, so far I have again focused on some well-defined areas or well-defined equivalent current dipoles that we're looking at. But as I said, actually the whole brain is active all the time. So when we do a measurement, it's not just the signal that we're looking at. It's actually all the underlying activity that is summed up at the locations where we measure things. It's not only that, but it's also other biophysical properties that we pick up from the body of the participant. And as I said, EEG signals is at the microvolt scale, but we actually have other electrophysiological parts of our body that generate way stronger electric signals than this. And this is, for example, the eyes, blinks, and eye movements, its heartbeats, and its muscle activity. And fun fact is, all these things we can measure the same way as we measure EEG with the exact same kind of hardware. It's just if we place it on the eye, it's called the EOG, so electrooculogram. If we place it above the heart, it would be electrocardiogram. Or if we place it at the muscles, it would be electromyogram. So EOG, ECG, and EMG. But that also, since it's basically from a physical perspective the same, it will be picked up by our EEG electrodes on the head as well, especially because these are much larger. So the brain activity that we're looking at, so saying in a typical event-related study, would be perhaps a few microvolts. The background noise that we have in the brain, I put noise in quotation here because it's still the brain activity that we're measuring, but it might not be relevant to what particular phenomena we are studying. That could actually be about sort of spontaneous activity, could be about 10 to 50 microvolts. So we're already a factor 10-ish larger than the signal we might be interested in. And when we then look at the physiological noise, so for example, the eye movements, eye blink, muscular artifact or cardiac artifact, which have these very typical patterns. So blinks have these very clear blinks. And when we start to look at the data, you will clearly, you're never in doubt of when a blink is occurring. Muscle activity is also very easy to spot. It's this very high frequent kind of noisy pattern. And cardiac, it's not always we see this in EEG, but sometimes we can see it as well. And then it would have these very stereotypical waveforms as well. And all these, similar to everything else we measure, is just summed together to give the actual measured signal. And these are usually can be from a factor 10 to actually 1,000 times larger than the original brain signal that we are looking at. So this is I guess all the practical sessions is just one way or another of figuring out how we deal with this and how we get back to the brain activity, the signal of interest that we are looking at. So that is why also when we just see the raw EEG traces, it can be difficult to actually make sense of this. We have to do some processing of this. In addition to that, what also is being picked up to various degree is kind of environmental noise. And this is here just used as a very broad umbrella term, that it could be electromagnetic noise that comes from, for example, computers in the room or power cables, light, or so on, which we will try to minimize through in our lab setup and so, but it will be picked up to some degree. Okay, so again, making it sound like we have these methods and there's a lot of things that kind of can go wrong and drown out the signals. And to some extent I can. And for the rest of this workshop, it's basically how do we optimize this so we actually get good quality signals and good quality measures in the end. That is kind of the basis for valid scientific conclusions that we would do or clinic applications or however it's going to be used. So just to give a final summation here is that when we look at the data, so we're doing some recordings here, now understand that what we are measuring here is the kind of summation of all the underlying currents, that each of these lines represent a specific electrode location placed somewhere on the scalp. And it's a mixture of everything, so both the signal that is relevant, so say if it was a task, that would be the specific activity sort of induced by this task. It would be the brain noise, I would call it, but basically everything that's going on in the brain at the same time that might not be relevant to the task. It would be the physiological noise and artifacts, and it could be some environmental noise that what they will seek into this. And with this, it's kind of the end from we started at the cell and ended up at how EEG actually look, and then we will go on with what do we do with the data, or practically how do we measure it and what do we do with the data from here. So any questions?